All right, so chapter 5 is all about solving systems of linear equations. 5.1 is specifically when we have two variables. And then the next section, we're going to bump it up to 3 variables. Now, in Algebra 1, you learned how to solve systems of equations in 2 variables. In Algebra 2, you did do systems of equations in 3 variables, but you used matrices to solve them, which was all computer and calculator based. We are not doing matrices again this year. We're going to go back to solving these things by hand. So to be able to solve 3 variable systems by hand, we have to have the skills for 2 variable systems, and then we'd be good to go. So let's talk about the 2 methods to solve a 2 variable system. The first one is called the substitution method. So if we're using the substitution method, kind of like with the word substitution or substitute, you're going to take something out and replace it. So the goal here is to solve either of the equations for one particular variable in terms of the other. So like you need y equals something or x equals something. Sometimes problems are already given to you as y equals or x equals. Sometimes we have to do those steps, but we're going to choose this method when that's really easy to do. The second thing we're going to do is we're going to substitute the expression found in step 1 into the other equation. So you're going to take what you've isolated and plug it into the other equations, taking out the variable, sticking in your expression. This will result in an equation in one variable. At that point, all we have to do is solve the equation for the one variable and then back substitute or plug back in the value from step 3 into the original equations, simplify to find the value, and then check your solutions to make sure that they work. So let's see what this looks like, and let's see if I nailed down my color scheme here. To solve a system by substitution, we're going to look for a variable to be isolated. Right away, are either of the variables isolated in the first or in the second equation? No, but do you notice that this variable is like almost by itself? There's no number in front of x, but there is a minus 2y behind it. So what we're going to do first is we're going to isolate the x by moving the 2y to the other side. So I'm going to have x equal to positive 2y minus 3. So I just took the 2y and I dropped it on the other side. That is my isolate step. I have isolated the variable x. X is now equal to 2x minus 3. What I'm going to do with that expression is I'm going to take the other equation, and where there was an x in that other equation, I'm going to plug in the expression that I've solved for x. I'm substituting it in. So that's my substitute step. Step 3 is to straight up solve for the variable that's left. So right here, the variable that's left is y. We use our Algebra 1 skills to solve for y. So I'm going to distribute. That's 10y minus 15 minus 4y equal to 9. We're going to combine our like terms. 10y minus 4y is 6y. And then add 15 to both sides. That's 24. Divide by 6 on both sides. That's 4. So, yes. So far we have isolated one of the variables, choosing the easy one to isolate, which in this case, x was already pretty much by itself. So we just move the 2y to the other side, substituted it in, solve the regular equation, and we're already halfway there. All we have to do now is back substitute the letter y into the original red equation. Okay. So the red equation from earlier, or the pink equation from earlier, was x equal to 2 times y minus 3, but I'm going to substitute that number 4 that we just got. This was my back substitute step. And once we back substitute, we're just doing 2 times 4 minus 3. 2 times 4 minus 3 is 8 minus 3, therefore x is equal to 5. So my solution here is a coordinate point that is the place where these two lines would intersect on a graph, but we're not solving these graphically, we're going to solve them by hand. And that's the goal of pretty much this whole unit, is to solve these things by hand. The answer here, solution, would be 5, 4. My stomach just growled so loud. Did anybody hear that? Wow. It was an angry growl. So again, substitution. I personally love substitution. I think it's really fun because it's just a whole bunch of algebra over and over again. You're isolating one variable, substituting it in, solving a regular linear equation, then back substituting into what you isolated to get the other equation or other variable value. Boom, done. Make sure your coordinate goes x comma y. Questions, comments, concerns? Step 5 does say to check the proposed solution into both of the equations, and of course I highly recommend that whenever you're taking a test, because then you know that you got the answers right, and we've checked solutions before, so I don't really feel like we need to show that step. This is the only example of substitution we're going to have today. Are there any major questions? That's a lie. There's an example of substitution later. I bet. Substitution is what a lot of people navigate towards when you're solving a system of equations, but another method. In Algebra 1, you would have called this the elimination method, but we're going to be calling it the addition method because really what we are doing is we are combining or adding the two equations together, and yes, it does end up eliminating a variable. So step 1 is to rewrite both equations in standard form. AX plus BY equal to C. That's like a prep step. Also a prep step, and you're going to see this one a lot. If necessary, multiply either equation or both equations by an appropriate non-zero number so that the sum of the x coefficients or the sum of the y coefficients is 0. Basically, you need to find or you need to create a function where there is one that has positive ax and then negative ax, or positive by and negative by, so that you have opposite coefficients for either your x value or your y value. Once you have that, we're on to the actual steps, and what we're going to do is straight up add the equations together in step 2. It's why it's called the addition method. The sum, because one of the variables will eliminate, is an equation in one variable. So just like before, then we get to solve the equation and then back substitute the value in. The back substituting step does require a little bit of solving, but it's still back substituting. Can I show you an example? So for number 2, solve by the addition method. Right now, I see that these are already written in standard form. So we have the x's, then we have the y's, and they're equal to numbers. Are either of the x's or y's right now opposites of each other? No, so we're going to have to make it happen. So just because I know where I'm going when we do 3 variable systems, here's what I want you to do. We're going to label this as equation 1, and we're going to label this as equation 2. And what we're going to do is we're going to force them to have opposite coefficients. I want to multiply the first equation by -4. So I'm going to do -4 times the first equation, which means my first equation becomes -12x. That's a big line, not -4. We're going to multiply it by 4, so sorry. It becomes 12x plus 8y equal to 192. Every single number in equation number 1 got multiplied by +4, not -4. Don't know who I was 5 seconds ago. Then I'm going to rewrite down equation number 2. Because now, if I look at these equations, now that I've manipulated the top one, do you see that now there is a coefficient where one is positive and one is negative? I have positive 8y, and then I have negative 8y. That's what we want. Once we have those opposites, that's where we go to the steps, and we're going to add these two equations together. 12x plus 9x is 21x. Negative 8x plus y plus 8y cancel each other out. And 192 plus -24 is 168. Look how quickly we got this down to an equation that we can solve. If we're solving for x, how do I solve for x? Yeah, divide by 21, bing, bang, boom, x is equal to 8. Once I have a value for 8, I need to back substitute it into either of the two equations so I can solve for the y value. So what I'm going to do, and this is a notation I'm going to use, especially when we go to three variable systems, I think it will be helpful. We're going to take the x and we're going to plug it into equation 1. You could have picked equation 1, or equation 2. It doesn't matter. But we're going to substitute that in. So it's going to be 3 times 8 plus 2 times y equal to 48. So we're plugging the x value into number 1. That's the notation I'm using, and this is a Miss Quigley notation to help explain what we're doing on the notes. 3 times 8 is 24. So it's 24 plus 2y equal to 48. We subtract 24 from both sides. We divide by 2 on both sides. We get that y is 12. So our solution to this system using the addition method is 8, 12. This feels more complicated, and for some questions it is, but these skills for solving a system by addition is really what I want us to nail down because it will help us when we do three variable systems. Okay, let me walk through it just one more time. I'm going to scoot this over just a little bit so the notation doesn't confuse you. This is x plugging into number 1. What I did first is I saw that equation 1 and equation 2 do not have opposite coefficients. So I forced it to. I multiplied the entire first equation by 4 so that this became positive 8y, and it would be multiplied. Once there are opposite coefficients, we can add the equations together straight down like an elementary problem. 12 plus 9 is 21. 192 plus negative 24 is 168. The y's cancel out. Divide by 21, divide by 21, we get a value for x, and we can back substitute that into either of the two equations and simply solve for the opposite one. Questions, comments, concerns? Could I have done something with?
Like instead of plugging in the 4, could you like plug in a 3 for 3 and 9?
Are you saying, so did I have to do 4?
Yeah.
No, if you find another way for these things to cancel out, you could totally do it. So I could have multiplied this top equation by negative 3 because then this would become negative 9 and these would cancel. So whatever you see first.
So the negative could be on top?
Negative can be on top, yes. It doesn't have to be positive and negative. As long as they are opposites, they're good to go. Okay, can we see a complicated example? Cool. This next one is a little bit complicated because first of all, what do those equations look like? Do they look like they're in the right form? No, so before I do anything else, because I know I'm using the addition method, I'm just going to rewrite these equations in the right format. Say again? They actually will not cancel because, right, the 17s would cancel, but the x's and y's wouldn't. I need an x and a y to cancel.
Yeah, but I'm saying like, because if you put it in,
Like solve for y or something?
if you're like moving the x and the y's over to like the other sides, the 17, if you leave them on the same side, they would just cancel.
They would, but none of the variables would. So it doesn't help me solve solve for the variables, but they do cancel.
So that's why I was asking if there's like a different way you can solve it.
So if I move these, this is what Leah's saying. She's saying if you line these up, so if I have 2x minus 7y equal to negative 17, which is standard form. I picked the 7 up, moved it to the other side. Pick the 3x up and move it to the other side. This is 3x plus 5y equal to 17. Yes, I totally see that those 17s would cancel. So it feels like we're doing the same step of elimination, but we're trying to eliminate a variable, not the constant. Trying to eliminate a variable, not the constant. Okay, so what do you guys see about these equations? Let me write them a little bit more lined up because I think lining them up is so important for this lesson that we got to get my handwriting right. 2x minus 7y equal negative 17. 3x plus 5y equal positive 17. Is there anything right away that you can see that we could multiply equation 1 and equation 2 by to get one of the variables to eliminate?
The first one by 5 and the second one by 7.
Absolutely. If we multiply the first equation by 5 and the second equation by 7, we would get the y's to be the same but opposite. So let's go ahead and do that. And so this feels a little messy, and that's okay. So what we're going to do, we're going to multiply 5 times equation 1 and 7 times equation 2 as our first step. This becomes 10x minus 35y equal to whatever 5 times negative 17, which is negative 85. Then we multiply 7 times those two, 7 times the second equation. This would be 21x plus 35y equal to 119. We had to multiply both equations this time, to get them to be opposites. So sometimes it's more than one. But now we take over. We do our adding. We're like, okay, great, the y's are going to cancel. They don't always have to cancel first, by the way. You can cancel x's first. This becomes 31x equal to 34. Trust the process. How do you solve for x? Divide by 31. 34 divided by 31 is some decimal that I'm not going to round, so I'm going to keep this as 34 over 31. Boom, I have my x value. Now my next step would be to back substitute the number x into the equation. But like, ew, do you want to actually back substitute the number 34 over 31 into one of these equations? You can. It will totally work. I don't particularly want to. So instead, and another option for you when you're doing addition is to multiply by a scalar again to get the other variable to cancel out. So if we were trying to cancel out the x's this time instead of canceling out the y's, what would I multiply the top equation by and what would I multiply the bottom equation by? Super close. I can multiply the top one by 3, and if I do 3 there and I just do 2 here, they'll be the same sign. One of them needs to be negative. So if I do this, 3 times the entire first equation is 6x minus 21y equal to negative 51. And negative 2 times the entire bottom equation is negative 6x minus 10y equal to negative 34. So repeating just the first few steps of addition here, of the addition method, is totally viable if you don't want to back substitute the number you have because it's kind of ugly. This time when we add these together, the x's are going to cancel. This becomes negative 31y equal to negative 85. And when we solve for y this time using basic algebra steps, oh look, I showed my work. I never do that. This would be 85 31s. So if you get a value for the back substitution that is pretty gnarly and you don't want to work with it like this one, you can just eliminate the other variable and find that the x value is 35 over 31 and the y value is 85 over 31. Or back substitute, trust your instincts with fractions and work with them through the whole problem. You'd get the same numbers. Questions, comments, concerns about addition method? We'll have lots of practice time today for you to ask additional questions if you think you're good now and then look back later and you're like, oh no. But of course, when we're dealing with systems of equations, so far we've only seen systems that have a solution. They have an ordered pair where the two graphs would cross each other. But there are options for special cases where solutions don't have exactly one place where the two lines intersect. So this is pretty typical. This is what we've been solving. The solution is the coordinate pair where they cross. But parallel lines never cross. So there will be options when there is no solution. And there are times when there are two lines right on top of each other. So you can't really tell because yours is not in color. But like technically this is that maroon line and the blue line right on top of each other, which means the lines coincide with each other. Let's see what that looks like, not graphically. Let's see what it looks like on paper. We're going to solve this system. Is this one set up for us to solve using elimination or with substitution? Is there a particular variable that's easy to solve for? Like x or y being by themselves in one of the equations? No, so this one would not be easiest to do with substitution. It actually would be easiest to do with elimination. So we're going to label them as equation 1 and equation 2. And we're going to multiply them both by a number so that either the x's or the y's cancel out. Whoa, good catch. What would I have to multiply the top equation by to get the x's to cancel out? 3. That'll work. Okay, so I'll multiply by 3. What would I multiply the bottom one by? Make a negative, because we want the x's to cancel out. So this would become, oh, never mind. We'll wait till after lunch. So after lunch, we'll figure out what it will become. Okay, before lunch, we got here where we were going to multiply 3 times the first equation and negative 2 times the second equation so that things would cancel. Let's go ahead and do that now that we're all full. This is 12x plus 18y equal to 36. And then we have negative 12y, x, minus 18y equal to negative 24. Some of you might see what's coming already, but when we add these two equations together, what's going to happen? Two things cancel out. The x's will cancel, the y's will cancel, which means we have 0 or nothing on the left side of the equation. And then we have 36 plus negative 24 on the right. So question for you, does 0 equal 12? Not in this type of arithmetic, it does not. So in fact, this answer, or this system has no solution. These would be parallel lines that never cross, but you would answer with the empty set symbol for me. So no solution. So again, if your variables cancel out and you're left with a false mathematical statement, that means that the two lines do not have any place where they cross and your system has no solution. Can we try another? Not yet. I see we're still writing. Okay, thank you for your honesty. Example 5 will be an example of a system with infinitely many solutions. We're going to solve it differently. What do you notice about this one? Specifically, maybe this equation right here. What is already going on in that equation? It's already solved for y, correct? So this is an indicator that we want to use substitution here. So what we're going to do is we're going to take that y value and we're going to substitute it in to the equation that does not have it isolated for y. Meaning we're going to do 15x minus 5y equal to 10. But for y, I'm going to use that isolated expression for y. I've substituted the y in. Instead of y, now it has the expression that represents y. We solve like normal, which means this is going to be 15x minus 15x plus 10. Ooh, are your spidey senses going off? What is 15x minus 15x? These should cancel out, yeah? So then I'm left with a mathematical statement that says 10 equal to 10. Is that true or false? True. So if your variables cancel out and you're left with a true mathematical statement, that's when you would answer infinitely many solutions or your fun and funky R representing all real numbers. Your textbook also has a third way to write this, and I will not require it. I'm cool with just the all real numbers symbol, but just to also put another option out there in set notation, you can say that this would be all x's and y's such that y is equal to 3x minus 2 and the set of all x's and y's such that 15x minus 5y equal to 10. And I don't know why anyone would write it in that format. That set builder format takes so much time and paper. You can just tell me all real numbers. Another reason we're doing this section entirely on paper, because I don't like the way those answers are written. I would prefer the empty set for no solution and all real numbers for infinitely many solutions. So our goal today is to really get these beginner skills down, because the next lesson is going to be 3 variables at a time, an X, Y, and Z. And if we can nail down, especially the addition one, solving a system with addition, then we're going to be in really good shape to not be overwhelmed next class period.